you may be familiar with images, and the pixels in the images are actually features. But we have to compute these features before we can train models with them. So once we have the features, we can train models with them. And we need a machine learning framework to do that. It could be a classical one like scikit-learn, or it could be deep learning framework like TensorFlow or PyTorch. But what you get out of that is the model. This is the function which will take an input. It could be the loan, the parameters for approving the loan, and the output will be a prediction, should this loan be approved or not. And these models are then served by the applications. So one of the problems that is frequently encountered, and it's one of the big challenges in putting machine learning models in production, is that the model that you're serving, so this loan application model, it requires features as well. It requires exactly the same features that were used when you trained the model. When you're training the model, you may have known that the credit score of the customer, if it's available, is very important. If that customer has products with this insurance company, it's important. The historical behavior of that customer, have they repaid their loans on time? Maybe external information we can get about credit scores for customers from third-party sources. There's lots of different features that can help us make that prediction. So one of the problems is, how do you get those features into the model that you want to serve? We can redo the feature engineering up here, like we have this little box showing it in red. And the problem with that is that potentially the features that we compute in our online application, that's taking the loan approval request, and it's computing maybe the information about the customer, their credit score, that might be okay. But then historical information about this potential customer, how many times have they repaid their loan in the last 12 months? Have they repaid them all on time? That information may not be available in the online application. So historical features, contextual features, it's very hard to get them in the application. And if you do write code in the application to compute them, it may not be exactly the same as the code that you use to compute the features when you were training the model. This is what we call serving training skew. And when you have serving training skew, then you have problems. It's very hard to debug those models. It's very hard to identify the root cause of prediction problems. And this is just generally not regarded as best practice. So I think at this stage, many people understand that this is not the way to go about it. The feature store will help us solve that problem. The feature store will fit into the ML pipeline as we can see it as a service or a platform where we go from our raw data on the left-hand side here. This is the data stores. So this might be your data lake. It may be Azure Data Lake. It could be the Blob Store. It could be Snowflake, data warehouse, or it could be an operational database. And these data stores, or it could be an event bus, have the raw data, and we need to extract that raw data and compute features on it. So we do need some engine for computing features. And I said our platform is open. In particular, the Hopsworks Feature Store supports any Python environment or any Spark environment to compute features. So if you have HDInsight, it's a Spark environment. If you have Azure ML Studio, that's a Python environment. If you have Databricks, it's a Spark environment. Hopsworks supports both Spark and Python environments for computing features if you do your feature computation in Hopsworks. And the features themselves can be cached then in the feature store. This is our feature store here. And they can be cached again for serving and for training. So this helps us remove this potential problem of model skew, of serving training skew, by computing the features only once. And then they're stored in the feature store, and they're dispersed to the online features store. And we have two databases in here, I should make clear. One is used by the model serving, and this is what we call the online feature store. It's a low latency database. In our case, we're using the database called MySQL Cluster, or NDB. And the inventor of it, Mikael Rönnström, works for us at LogicalBox. And we have a second database for storing scalable large volumes of features or historical features for training. And we're actually using the data warehouse called Hive, which ultimately would store data on Azure Blob Storage. So it's the Azure Blob storage service. It's called Azure Blob. Okay, so the features that have been computed will be stored in both this low latency database, NDB, and then this scaled database, Hive. We'll have the historical features in Hive, and then we have the latest values of the features in the online feature store NDB. And then the models that we're serving in production can always read the latest values of features. So we can read, for example, the credit score of a customer, the historical information about payments they made. Maybe if it's a retail application, the number of clicks this user has made on the website in the last 10 minutes. There's many different features we can retrieve from the feature store here. And then when we're training models, but also in batch applications, when we're doing those analytical models that we want to make predictions with, then we go to Hive and we can pull out the historical features to create training data. And that training data we can use to train models. So all of this, this infrastructure I'm presenting here, it can be found in the cloud. We're talking about Azure today. You can also have on-premise. There are other clouds, of course, like AWS and GCP. But our particular feature store is available on all of these platforms. Okay, let's move on. So features that come into the feature store are not all the same. One of the points that we see straight away is that the sources of the data, so data may come from an event bus, and it may, for example, user clicks we're trying to ingest into the feature store, and we want very low latency updates to these user clicks. We want to know every 10 or 15 minutes how many times the user has clicked the website. So we need an always-on compute engine to compute, because we're going to be always receiving all the user clicks and always writing them to the feature store. So you can use, in our case, for example, Spark Streaming, which is a streaming engine to compute your features as data frames. So this is the first point about our feature store. The main API for ingesting data into the feature store is a data frame API. And that could be a Spark data frame, or it can be a Pandas data frame. So if you're writing your feature engineering code in Python, you'll work with a Python Pandas data frame. And if you're writing your code in Scala Spark or in PySpark, you'll write as a Spark data frame. So your data may come and be updated very frequently, let's say every 10 minutes. We might do it for user clicks. And we maybe get updates from databases once per hour. And maybe we'll get updates from data warehouses once per day, and maybe from a data lake once per week. So you can have different sources require their features to be recomputed and updated at different cadences or different rates. And you can have different engines that you use to compute these features. So some of the things that you want to do when you're computing these features is you want to make sure that the data is valid. So in our particular feature store, we have support for a library called DQ for doing data validation. So you can define reusable rules for validating data that's ingested into the feature store. We also want to monitor the data that's coming in, the features that are coming in, and make sure that if the values of the features change significantly over time, we call that the feature drift. The features are drifting in value. You would like to alert and say, well, hang on, there may be a problem here in the quality of the features coming into the feature store. And I said earlier we have both the online and offline feature stores, but in our particular feature store, we abstract away that complexity. You don't need to worry about writing your data frame to both the online and offline feature stores. The platform takes care of it for you. We present an abstraction called the feature group, FG, and the feature group is effectively a table or a data frame that you're ingesting. You can think of it as being having a schema. It has each column in the schema is a feature, and you can decide whether this feature group is stored in the online, the offline, or both. And we can see that the downstream uses of the feature store, we have our online applications that want to retrieve values from feature groups. They're going to retrieve what we call a feature vector, a row of features, and that row of features is appended to any real-time features that come in. And then you send that to the model for predictions. And then the other downstream users are batch applications and data scientists who want to train models who will pick features and reuse them. We're going to join those features together to create training data sets. So then we want to reuse the features in the feature store across many models. If you don't reuse features, what happens is every time you want to put a new model in production, you'll need a new pipeline to create the training data for that. So then here with the feature store, we're decoupling the number of pipelines we need from the number of models. We can have as many models as we want reusing these feature groups that are in the features that are located in feature groups. We still kind of a fixed number of pipelines feeding the feature store. Last point I'll make here is that if you do have features, and we do meet customers and prospects who have very low latency requirements on feature engineering. So sub-second requirements. You have data coming in, and you need to do real-time engineering on that data. You need to compute those features and make them available to the online application. So sometimes you will not push those features to the feature store first and pull them out. Instead, what you can do is you can make them available directly at the online application. And we have a platform which we haven't open sourced and talked about. We've talked about it at the Spark Summit, but you can contact us if you're interested more and look at the talk. It's called HOF, that does real-time feature engineering on Hopsworks and synchronizes the features with the feature store. So we're going to look a little bit at the API for accessing Hopsworks now. It's called HopsFS. And HopsFS is because we have Spark and we have Python clients. It's a single library, works both for PySpark and for Python. It's also available for Scala, Java. And what you do with HopsFS is you just pip install it. And in this example, we're using PySpark. So what we can see is that we're reading up some data from, in this case, the Azure Data Lake Storage Service. And we get back a data frame. So Spark is reading up this data frame containing this rain JSON object. We do a little bit of feature engineering on it. In this case, we're just normalizing this precipitation column or feature that's in that feature group or that data frame at this point in time. And we're creating a feature group that we're going to save this data frame into. In fact, that should be DF. I can see a little bug on that slide. So that should be DF, if for those of you who are paying attention. So the feature group that we're creating here, we're calling it rain. We can see the first thing we have here is that we have a version. So this version refers to the schema. So our feature groups are stored in the offline feature store as Parquet data. And when we have time travel enabled, that I'll talk about in a minute, we use hoodie on top of this metadata on top of Parquet files. But Parquet itself doesn't support schema evolution very well. So what we do is at the feature group level, we enable you to evolve schemas of feature groups. That means that you can run a production pipeline with this rain feature group. You can use it to ingest features into the rain feature group. You can then use that feature group for serving and also for training. And then you can have a new version, like version 2, where you can develop a new version of that feature group. Maybe you're going to drop some features, maybe you're going to add some features or change the implementation of features. So maybe you have an embedding and you'd like to have a new version of the embedding. So in this case, we create a new version and then we backfill the new feature group and we can then use it in pipelines. And when we're happy, we can switch over from the old version to the new version. So versioning is important for schemas of feature groups. And we can also search for feature groups, so we can have a good name description of the feature group to make it easier for other users to find in the feature store. The entity ID for this feature group, which many other feature stores use this term of entity ID, we don't use the term entity ID because it's not a single ID. You have a primary key associated with a feature group, and the primary key may have multiple parts. In this case, we have date and location ID. So location ID is logically the entity ID here, but the date is also part of our primary key in this particular feature group's case. Now, the final thing we have here is that we indicate that this feature group will also be stored in the online feature store. That means that it'll be synced to both the offline, which is enabled by default, and the online one. Finally, we save the data frame into it. So that's ingesting data into the feature store. It means that we're going to store a copy of this data frame in the feature store, and then it's pre-engineered features and can be used for training and serving. It is also possible to take pre-engineered features that maybe are on your existing data warehouse, or maybe it's on your existing data lake, and mount them as what we call on-demand feature groups in the feature store. So an on-demand feature group is one where we do not store a copy of the data in our feature store. We just store the metadata. So in this case, what we're doing is we get a connector to Snowflake. We'll show how to define a connector in the feature store soon. And we create an on-demand feature group. And in this case, we have versions for them. But this case, we're saying, here's how to get the data for the feature, this particular feature group. We're going to just select all of the columns from the telco table, and it's going to connect into the Snowflake cluster, and there'll be a table called telco, and all of the values in there will be our on-demand feature group. when we indicate the storage connector that was defined, that we retrieved from the feature store here. So there's obviously no credentials stored in here. The credentials are stored securely in the Hopsworks feature store. We can still have statistics over feature groups. So that's one of the things we'll see in the demo, is that when you ingest features into the feature store, we compute statistics over them so that you can look at the distribution of feature values, descriptive statistics for features, mean, maximum, min, standard deviation of feature values. And we can still do that as well for on-demand feature groups. It requires a full pass of the data to compute them. So you can turn it off if you want. And then finally, we save this to the feature store. So the other types of sources you can have, so it can be any JDBC source for any backend data warehouse that you may have, or database where your data is located, or you can use Azure Data Lake Storage on Azure, or S3 on AWS. So it could, for example, be if you have Databricks on S3, you could have a Delta Lake store. Let's have a quick look at an example at how we define these feature store connectors. This is a feature store on Hopsworks. So what Fabio is doing here, and Fabio is our head of engineering, he did this quick video, he's basically defining a connector to Azure Data Lake. And you can see there's a number of parameters you have to fill in here. You have to have a service credential, an application ID, a directory ID, an account name, and then the container inside this particular storage connector. So the container is like your directory inside it. And you can see there's also two versions of the Azure Data Lake. You have version 1 and version 2. So version 2 is obviously the latest one. So Azure Data Lake, if you're not familiar with it, it has a HDLS API, but the data is stored ultimately in Azure Blob Storage. And in fact, it's very similar to the file system that comes with Hopsworks called HopsFS, which again stores the data in the Blob store in Azure. So when you install a Hopsworks cluster on Azure from Hopsworks.ai, the storage is decoupled from Hopsworks Feature Store. You're storing the data in the Blob store. So in this case, like what's showing now is how you use this connector in code. I have an example in the next slide, so we don't need to really look through this. But what you do is you get your I had an example in the previous slide, I should say. With that connector, we can then write out, for example, training data sets to Azure Blob Store or the Azure Data Lake. So let's move on. So if I have a feature group and I've ingested data into it, I may want to keep ingesting data. We call that incrementally updating the data in a feature group. Your pipeline might run every hour or every day to update the data in that feature group. So if we look at this example here, what we can see is that we can do an update by computing the changes in our data source, wherever the data is coming from, into this thing we call an upsert data frame. So this is the new data we're going to ingest into the feature group. We get our feature group, and you can see we've supplied the version number here. So it should be version equals 1. We can look at all the previous commits in the feature store if we want to, if we're curious, and then we can just insert this data frame. So you can see it says this word upsert. Upsert means either update or insert. So the data that's coming in will either be appended to the feature store, or it will, to the feature group, I should say, or it will update in place data inside that feature group. You can also delete data, which is very important for GDPR compliance. So you can see here, this update creates a new commit in the feature store and a new timestamp associated with it. In fact, underneath this, what's happening is by default, we're going to use an engine called Apache Hoodie, which was developed by Uber, which provides the support for incremental ingestion of data and asset updates, and also time travel. This is what time travel is here, where the ability to read the state of the feature store as of a point in time. We can say, hey, give me the state of this feature group as of this point in time. So we get the data that had accumulated to that point in time. We can also ask for the changes in a given interval. So we can say, for example, in this interval, I would like to get all the data that was ingested into this feature group. And this is, again, what we call time travel. In the next version of the Hopsworks Feature Store, we're also going to support Databricks Delta as a backing technology for this time travel enabled feature groups. So that's ingesting data into the feature store. What if I'm a data scientist and I want to use features in the feature store to create training data? So a data scientist will firstly like to do exploratory data analysis. We'll look at that later. But let's assume this data scientist has identified 3 feature groups that contain features of interest. So we have this rain feature group we saw earlier, but another one called temperature feature group, another one called location feature group. And we're going to join them together into a data frame. So this data frame can be a pandas data frame that you can train your model with directly, or you can materialize it to the file system as we're doing here, and save that, for example, to your Azure Data Lake bucket or container, or you can store it on the file system that comes with the Hopsworks platform. So if we look first at this join, what's happening here, we have a query planner inside our HopsFS engine, which will look for the largest overlapping set of primary keys between the feature groups being joined together. So for example, if location ID is common amongst the feature groups, it will join them on that particular feature. You can override the query planner and say explicitly join on these columns. So it's quite a flexible mechanism. If we differentiate this with, for example, the AWS SageMaker Feature Store, in their case, they require data scientists to write SQL queries to do this. In our case, we can also do SQL to do this if we want, Spark SQL, but we're providing a nice Pythonic API for data scientists. So it makes it easier for them to specify these queries. And other things that are common, you'll select this subset of the queries, or call a projection over them, and not all of the features in a given feature group. So once we've got together the features that we want, we've joined them from different feature groups, we need to create a training data set, which is our next abstraction. In this case, the training data set, we're specifying its file format to be tfrecords or TensorFlow records. So this is the native file format for TensorFlow. And we have a random split of the data that we're going to save into 70% training, 20% test, and 10% validation data, so that you don't need to do that split yourself afterwards. It'll be pre-split for you. So what's really nice about this is then we can easily just save out that data that we read from the different feature groups and join together to that location in the file system. You can see we haven't explicitly specified a connector, but we can say, hey, this is going to this Azure Data Lake container. In our case, this will store to the file system on our HDFS file system called HopsFS and Hopsworks. But once your data is in some file system, then if you want to use TensorFlow to read up the data, you can just do the following. You can just basically say, hey, I have a training data set, which has this name and this version, and I'd like to read up the split called train. And you can change that split to be test or validate. And what you'll get back is a TensorFlow data set that you can use directly in your TensorFlow application. So if you want to change your training data from TensorFlow to NumPy, because you're going to train with PyTorch, or CSV because you're going to train with scikit-learn, it's very easy for data scientists. It makes it very productive. They can just change tfrecords to CSV and off they go, or to NPY, NumPy, and off they go. They get their training data in a different file format. Like I said, if you want to store this data explicitly in the container on Azure Data Lake, well, then you can specify your connector to Azure Data Lake, like we have here, and then the data will be stored inside this connector. And the connector also supplies the container name, as we saw in the demo. So if we move on from there to the online feature store, our online feature store has a JDBC API. It's MySQL cluster, as I mentioned already, or NDB. And the way it works is that we have these number 1 and number 2. Applications, what they typically do is they'll need to build a feature vector, and they go to the online feature store to retrieve the features that they need. And this is the row of features, and that basically they may need to join with some features that have come in real time in the application. And then they send that feature vector, and has to have the same order as the training data set. The features need to be in the same order to the model for prediction. So sometimes that'll be a NumPy array that you send. And this can actually all be done in the model. If you're using KF serving, kubeflow serving, which will be included in the next version of Hopsworks, we can actually do this retrieval of features from the feature store and the joining of them together into the feature vector and sending that to the model. You can do that in your transformer layer in kubeflow serving, but often you'll do it in the application. It depends if your model is being served over the network or if it's embedded in the application. So SQL is a very powerful way. It means you can write your client in any language pretty much. You just need a JDBC connection to the feature store. It's going to a MySQL server. But you might also want to do this in a language-specific API because it's easier to do it. So what you can do in the next version of the HopsFS library is that you can basically get back an individual feature vector by just supplying the input keys. This is the primary keys for the feature groups that make up the training data set. So when we had our training data set and we joined together features from different feature groups, we just need to supply the primary keys for those feature groups. And then what we'll get back is a row, an ordered feature array. And then this array, this Python array, which is correctly ordered, it's going to be the same order as the training data, and we can send that to the model and convert it into an NumPy array. We obviously don't want to get back the label for this trained data set, so the label is dropped from us. And then that code can then make it very easy for you to write serving code that is actually independent of the features. If features are appended there, you don't need to go and rewrite that code. It'll return the correct set of features, and you send those to the model. And if your model is updated and the trained data set is updated both correctly, then it will continue to work. So let's put all this in context, and we're getting near the end of the slides. You do need, your feature store needs to exist within the context of a end-to-end machine learning pipeline. We talked a good bit about feature engineering, and you need a data science platform to create your models, and you'll need some model serving infrastructure as well. And these in Hopsworks, these can be any platform. You can have the feature store alone. That's this thing here, and you can do feature engineering in any Python or Spark environment, and you can do your model training in any data science platform you want, and you can do your model serving again in any model serving infrastructure that you like. One way of doing it, if you did it in Hopsworks, you can do everything in Hopsworks, is you can do your feature engineering even in jobs, Python jobs, Scala jobs, or even notebooks. And the selection of features and the creation of training data sets, that often will be a notebook in our platform. And the training of models and any hyperparameter tuning and experimentation that you do, again, can be done in notebooks. And then the validation of models, testing and deployment of models, again, could be a notebook. And we can orchestrate all of these in Airflow. We're not going to talk about this today, but that just gives you an idea of the capabilities of the platform, that data scientists can really put models in production, and they can do it even with notebooks. They can write production pipelines for taking data from the feature store and deploying production models from there. We can see here that this is not an end-to-end pipeline. We have two pipelines. We have the jobs that feed the feature store, and they run at their own cadence, and the training pipelines are separate beasts. So let's have a quick look at how we integrate Databricks with the Hopsworks feature store. So Hopsworks typically will be deployed in its own, it's not going to be VPC, that's Amazon terminology. It's going to be deployed in its own resource group in Azure. And Databricks will be also deployed in its own resource group. And we use VPC peering to connect them together. And we can have a quick look at that. Once you've deployed Hopsworks from Hopsworks AI, the managed version of Hopsworks, we have quite a nice and easy way to configure your Databricks cluster, because the Databricks cluster should point to the Hopsworks feature store. And we need to install this HopsFS library and another library called Hops. And there's a couple of Spark configuration changes that need to be made. But instead of you having to do that by hand, what you can do now is that you can just create an API key, a token on Databricks, and you do that by going to this Databricks button and to the settings, and you create your token, copy the token, and then you paste that token into Hopsworks. So we have this new integration section here, which gives you integration for Databricks, but also instructions for how to integrate the feature store with any external Spark cluster. So in this case, we just put in the URL to our Databricks cluster, and then this token that we copied from over there. And then we on the next page, we just then click configure. And what it will do is we select the user that we want to configure it for. And what it will do is it will basically configure that Databricks cluster so that it points to the Hopsworks feature store, and that we install the libraries that need to be installed. So that makes it very easy, a self-service way of configuring your Databricks clusters. If you're using Azure ML Studio, it's a little bit easier. It's a Python client, so it's not a Spark client. So what you do is you basically just have to install the HopsFS library, and then you need to connect to the feature store. I'm going to demo and go through this in a bit, but once you've connected to the feature store, you can then do exploratory data analysis and get features and feature groups, create trained data sets, and so on. Okay, So this is the bigger picture. I'm going to skip over this, but this is quite a technical picture. If we just stick to what's related to the feature store, here we can see that obviously we need to compute features and ingest them. We need to use them for training, and model serving needs to retrieve these features. But even model monitoring could benefit from the feature store, because you can get the statistics for training data sets and compare them with the live traffic on the model to look for things like data drift in model serving. And we can also log predictions that are made on the model to the feature store and use those then when the outcomes arrive later as new training data for models. So Hopsworks is available as an open source platform with the GPL v3 open source license model. It's fully featured. You can do anything in it. And there's an enterprise version of it that has some additional features. It has a single sign-on with LDAP, Kerberos, OAuth 2, and GitHub support and GitHub integration, I should say, and Kubernetes integration. So you can do model serving on external Kubernetes cluster or run Jupyter notebooks or even Python jobs on external Kubernetes clusters. We also have then the managed version of Hopsworks that runs on Azure, and it has some additional features such as elastic clusters that can scale up and down, and you only pay for compute. You can do backups of clusters, upgrades, single sign-on, and Kubernetes integration. Although Kubernetes integration on Azure is not there today, it's there on AWS. It will be there within a month or so. Okay, let's have a look then first at the managed version of Hopsworks, which is called Hopsworks.ai. You can go here today and you can register your account here, and you don't need a credit card. And okay, we have a question here. Can you restrict access to 2 specific feature groups? Yes, we'll get to that in a second. So we have a security model called, based around this abstraction called a project. You can think of a project as being a production feature store, development feature store, and we can give users restricted access to those different projects. And there's role-based access control within a project. So you can have a read-write access role called the data owner, and then a read-only role called the data scientist. I'll get to it in a minute. Okay, so you want to register there, and you'll get a demo or a playground cluster that you can play with, but really you should connect it to your Azure account. And if you connect the platform to your Azure account, if we click on settings here, we can see here that I've connected it to both my AWS and my Azure accounts. And there's a tutorial here that you can open to find out how to do that. I'm not going to go through it here, but basically you need to create a service principal, grant some permissions, and then get a subscription ID and tenant ID, and then you're done. So once you've done that, then Hopsworks AI, this cloud platform, it can basically, you can create clusters. So we have this button here, create cluster. You can see I have 2 clusters. This one is stopped. This one is started. This one here is available, accessible at this URL. I've opened up the online and offline feature store, and there's a couple of other services that I've opened up as well. I've made no backups currently, but the cluster itself, we can scale it up and down by removing and adding workers, and we have some more information about it there. So just a little bit more before we finish here, you can add and remove members to your account here. So you can add people to your cluster. You can do backups, and then we track usage of the cluster. So right now, if we look at the usage, you get, I think, $4,000 of free usage to get started. It will cost you to launch your own virtual machines on Azure, but otherwise you're okay. We won't charge. So the create cluster here, if we look at that, I'll just briefly show you. There's a lot of documentation on this, but I'll give you a basic overview. You basically configure your locations wherever your Azure data center is. You'll need to create a resource group in advance, and you'll need to also ensure that either your subscription or resource group has a custom role, and that's in the documentation. And then you'll need to have a storage account created as well. And you can give any container name, and it'll create the container in that storage account. A couple of other things in here. We do integrate with Active Directory and LDAP, so you can connect in here if you want to manage the users in the cluster from LDAP. And then there's the virtual net you're going to install the cluster in, and the subnet within that, and then security group, which we can create for you, or you can configure yourself. So we do require some permissions on your Azure account to do these things, and you can get a restricted set of permissions and perform some of these steps by hand if your IT policies require you to do so. So when you press create cluster, it creates the cluster and you get something like this. And now it logs me in, and this is the Hopsworks platform. I mentioned already that we have this grouping of called projects. It really is a security model, and really what's inside a project. And the project could be a production feature store. It could be a development feature store. You could have a staging feature store. You have a set of users in there. You have the data for a feature store, and we also can have programs. So feature engineering programs can go in there as well. You can, of course, connect it to GitHub, and your programs reside in GitHub as well. So if you want to follow along with what I'm going to show here, if you click on the feature store tour button here, it will actually create this project here. And it creates a project and it runs a job and pre-populates the feature store with a number of features. So I'm going to click on this button here to bring us into the feature store, to bring us into the project. And we see there's quite a bit more inside here than just the feature store. The feature store is just here. You know, we have utilization of the cluster, membership. If we're doing feature engineering in Python, we have very nice support for installing and maintaining your Python dependencies. So we have a conda environment associated with each project. There's also a base Docker container underneath this, a base Docker image, I should say. And the conda environment is layered on top of this base Docker image, and we compile Docker images based on the libraries in your conda environment when you create a job. So when you create a job, you get tied to the Docker image that is the layer of this conda environment when you create the job plus the base Docker image. So that makes your jobs immutable and has immutable dependencies. And it also means that if you have multiple projects and different projects have different requirements for libraries and so on, you can easily move those feature engineering jobs across different projects without requiring data scientists to write Docker files. You don't need to write Docker files. You just go in here to Python, search for your libraries. You know, say I want this Panda, some Pandas variant. There are not just one Panda library, but there's a bunch of them. You can install it. You can upload wheels or egg files, and you can even install libraries from Git. And this is the set of pre-installed libraries that I have in this particular project. I mentioned you can manage membership of the project. So in this case, I can add maybe a new user in here if I want to. I'm not sure if there's any users in here. I think there's one beginning with B. No, is Aura there? Okay, I don't know if there's anybody in here in this particular cluster, but we can basically change the roles from data owner to data scientist at that point. So you can remove and add people to the project as requiring who needs access to the project. We have some settings for it, some GDPR compliance issues, and the file system underneath it is available here. I'm going to skip over Airflow models and experiments. They're really related to machine learning, but we'll go straight into the feature store. So in this particular feature store, I have quite a lot of features, not a huge number, 116, split over 15 feature groups, and I've created 6 training data sets. We can see there's some storage connectors in here already, and the integrations I talked about earlier, Databricks, and then if you have an external Spark cluster, you can find some information about how to integrate there. I'm going to start on the feature groups, though, to begin with. So here's a bunch of them. I think the players features was one of them that's created in the tour, so I'll start at that one. Firstly, we can tag these. For governance, you can say this is PII, for example. You can define your own tags, user-defined tags, and then it makes it searchable. You can search then, free text search across all of your feature stores. You might have production, you might have, if I decide PII here, it finds all of the tags that match. And I can search also based on descriptions. This is really nice for both governance and for enabling users to free text search to find any ongoing work on features, not just ones that are running in production. So maybe you have a development feature store here in a different project, and there's some new features that are going in there that someone's developing. Well, we can find them in here. Even if we don't have access to the project, we can see them in the metadata and request access to them then. So let's go back. We were looking at the feature groups, and I think I looked at games features first. You can see, firstly, some of them are cached, some of them are on demand, some of them are in the online feature store, some of them not. And we have different versions of the schemas. If we look on the right-hand side here, we have a number of buttons here. The statistics shows us the pre-computed statistics over the features that have been ingested. We also have a feature correlation matrix that we can kind of briefly look at here. That's pre-computed again. What's interesting, I guess, is for the hoodie feature groups, when we do incremental ingestions of data, and if I click on this one called economy, I see this economy feature group, and if I click on the statistics, we can see that in this case, it didn't draw the distribution plots, but that's okay. But we can see that every time we do an incremental update, well, the actual, we recompute the statistics. So you can go back in time and find the statistics and compute feature drift based on how those feature values change over ingestions. You can get a preview of your data. In this case, this is a hoodie feature group. So in fact, the preview we can see here, we can also just look for a particular partition, which if we have a large volume of data is great. We can change the number of rows. And if we go back here, let's look at this one here. We also have a way of doing data validation. I'll skip over that. We have the job that was used to compute this feature group. We have provenance, which is very interesting. I'll show that in terms of training data sets. But provenance basically tells us which training data sets were used to create this particular feature group. So in this case, it says none. So let's have a look at the training data sets. We'll pick this one here. And again, we have the statistics computed over it, and we have splits and so on. But if we look at provenance, we can see, oh, these feature groups we used to create this training data set. So we're maintaining information about the linkages between the feature groups and the training data sets that are used to create. And if you create models or train models or platform, we also store those linkages. So the lineage between models, the experiments used to train them, the training data sets that were used to train the models, and then the feature groups that were used to create the training data sets. And we can also use tags if we even do feature engineering outside the platform and ingest the data to indicate where the data comes from so that we can continue our lineage to external systems. Okay, so that's you get a quick overview of how people access the feature store internally. I have some notebooks. We have support for running jobs here, and I'm not going to go through the jobs here, but you can create Spark, Python, Flink jobs even. And we have notebook support here. So I have a notebook already running. That's this one here. And there are many notebooks for HopsFS. We have, I think the starting one is this feature engineering notebook I just ran earlier. And it just takes some raw data that it's reading in, does some feature engineering. This is feature engineering that we're doing on that raw data, creates feature groups, and add some tags. We can add tags to the feature groups from the notebook. So there's also a notebook for using hoodie. It's called time travel _Python. There's one for Scala as well, and it does the incremental updates. And then we can see here we're doing some point in time reads as well. So reading for particular commits or particular points in time in data. There's also a notebook here for showing you how to create train data sets and how to do feature exploration. So being able to do exploratory data analysis from within the feature store, being able to see what features are available, preview values for features, even look at, for example, the primary keys for feature groups and partition keys and so on. So I think I won't go through these in too much detail because you can, if you register in the platform and try it out, these will come with the tour and you can just run them in your own time. So what I'm going to do is I'm going to move over and look at how we integrate Hopsworks Feature Store with external platforms like Databricks and also like Azure ML Studio. So let's go back and look. So I have them open in this browser here. Okay, so it seems green. I just started attached to this cluster before I started here. So I'm on Databricks here, and we can see we have this cluster called Gym Webinar. There are a few changes to it that we made when I ran that configure step that I mentioned earlier. So we went in here and I pressed this, not storage classes, integrations. So how did this one? Maybe it wasn't this one. It's this one here. Let's have a look. Okay, so we can call it get clusters in any case, yeah. So you can see I have a couple of clusters here, one's terminated, one's running. So I just need to, I can decide to configure it for my user in this particular case, and I press the configure button and it'll actually restart the cluster because to install those libraries in Databricks, you need to restart the cluster. So it'll make a couple of changes to it, restart it, and point it at this feature store. So the kind of changes it makes are it installs this library, HopsFS. There's a init script that it adds to the cluster as well. And if I can scroll down here, which I don't think I can. move this out of the way. We have advanced options. So down here, it adds some Spark config values and it adds an init script in there. So rather than do those things by hand, pressing that button will set up that cluster correctly for you. So this cluster is running, and I have this notebook that I started earlier on called Feature Exploration. So let's talk our way through it. So what we have at the beginning is we're importing the HopsFS library, which is already already installed on Databricks, and then we're going to connect to the feature store. So this is the domain name of our feature store. So I just got this by going back to the feature store here and copying this domain name here. It's the same way as Databricks identified their clusters. And then we specify the project name. So this project name here, we can get it here. I can just click it and copy it from here on the project name. And then we have the API key value. So you shouldn't do this. Don't do this at home, folks. You should get your API value from a key, or you can get it from a secret store, which is a secure way to do it. But just when you're testing, you can paste in an API key here. So where does that API key come from? Well, we have to create it in Hopsworks. So we have to go to the settings here. And in the API keys section here, what I need to do is basically fill in the name of the key. So I'm going to call this Databricks Gym, and I'm going to give it scope. So the API key doesn't have to access all services in the platform. We can restrict it to just say the project. We want to go inside a project. We're going to access the feature store, and maybe I'll run a job as well. So I can create an API key for that, copy that API key, then I can just close that dialog. And we can then paste that API key into a file, typically would be a safe way to do it, and then reference the file name when you're connecting. Okay, so this one connected here. And then what we can do is we can get a feature group. We can see here that it's giving me a warning saying you didn't add the version number. So you should, best practice is to add the version number, of course, because if you want to write production code and you're going to have that feature group evolve over time, then this code will continue working even as you switch version from 1 to 2 to 3. So we've now got the feature version, and we can do, we've got the feature group object, the sales FG object. And this sales FG object basically is our feature group. And if we type show on it, it's going to connect to the feature store. It'll retrieve a data frame for the data inside that particular feature group, and then it displays it here, the first 5 rows of that data frame. We can also, in this case, it's doing a filter and just getting we can apply filters to that data frame as well, where we basically get the table and only get the rows where we can see the store name is 20. So the store ID is 20. So it's kind of like doing an index on it. We can get some more description of the feature group, in this case, the primary keys and the partition keys to find out what they look like. We can also do, as I said before, we don't need to retrieve the entire feature group. We can just retrieve, in this case, 3 of the features or columns. And then we can join feature groups together that we talked about before. So data scientists can say, well, I've got 2 other feature groups, sales FG and exogenous FG, and we can look at those back in the feature store here. If we open up here, we have, in this case, sales. This is our sales feature group, and then we have the exogenous one. And you can see there's 3 different versions of it at this stage. And we're getting a warning because we didn't supply the version number again. And in this case, it's going to take this feature group. We can have you can have a preview of the data if you're curious and open the 2 of them. We didn't compute statistics for it. You don't have to compute statistics for them. You ingest them. And you can see also this feature group is available both online and offline. So you can actually get the data from the offline one or click online and it'll retrieve from the online, which is obviously a bit faster. So, at this point, you can do a bunch more queries. You can join more data. You can create more trained data sets, join multiple feature groups, and you can even do pure SQL queries in the feature store. So you can actually write SQL in here and it'll execute Spark SQL against the feature store. So that gives you an overview of how Databricks works and how we can access the feature store from Databricks. We can do feature engineering in Databricks. We can also create trained data sets, which data scientists would typically do. If we go to Azure Machine Learning Studio, that we can see here in front of me here, what we can see here is I'm using the notebooks from Azure Machine Learning Studio. And I created a notebook, a Python notebook. And in this case, what I'm doing is I just import let's run this here. So we're just importing the HopsFS library. We're connecting to the feature store, and then it says call, and then I'm just going to just look up a particular feature group here, and it's giving me some error. Okay, so maybe I need to restart this kernel. Let's restart that kernel. I think I've done something with it earlier on, as usual. But basically, in this case, what does it restart, run the cell? Okay, we try and run this cell again. So basically, what you can do again is the same as we were talking about in Databricks. Typically, feature engineering is done in Python or Spark. Often we find people use it in Spark or PySpark. So in this case, we can see what happened was we went to the feature store. We got back a data frame referring to the feature group called attendances FG. And so we got back the feature group, and then when we show, it'll materialize a data frame for it and return the first 5 rows. So we can do that, of course, for many different feature groups that are available in the feature store. And it's very similar to Databricks. Okay, so at this point, I think you've gotten a feel for what you can do at the feature store, how you can integrate and access it from different platforms. There's a little bit more details if you wanted to look at how to connect them with the VPN. I can show briefly what you need to do, but it's in the documentation. But basically, what you'll need to do in Azure Databricks is that you need to what you'll need to do is create something called VPC peering. Which is somewhere not in here. Okay. Yeah, we have this here. We have this virtual network peering. So I created a virtual network peering to the Hopsworks cluster, and you'll need to create that on the virtual network that Hopsworks is installed in as well. So that's really all you need to do to connect them so that they can securely talk to one another. So with that, I think I'll look back and see if we have any questions. I know we're out of time. We're at the top of the hour nearly. So I think, yeah, we asked the question, can you restrict access to specific feature groups? Just to repeat on that question, we have memberships in these projects. So, we can, sorry, we go back to members. So I can give the users I want to access. So I think there was a Ricardo user in here, maybe not. Okay. And you can add different users. So we have this person we can add as a data scientist or data owner. And let's say we add them as a data scientist, then they'll have read-only access to this particular feature store. And that way, when a user logs in, they'll only see the projects that they're a member of, and they won't see all projects that are in the system. Do we have any other questions there?
Hi, Jim. We got some questions. Thank you for the presentation. So we got a question that after my 4,000 credits, it's over. Yeah. Do I pay by use or by license?
Yeah, you can pay by use, in fact, and the payment it's similar-ish pricing model to Databricks, but maybe a little bit cheaper. And there is an enterprise option where you can buy bulk credits with discounts. So you talk to our salespeople to get access to that. What we're looking also at ways of maybe encouraging people to promote the use of it, so that if you promote the platform, we can give you some free credits. And if you're interested in doing that, you can reach out to us, and we can see what we can do.
Okay, I think we have time for one more question. How many requests per second can Hopsworks handle?
How many requests can Hopsworks handle? I mean, so it depends. When we say requests per second, we typically talk about the online feature store, and I guess that's what the questioner means. So the online feature store is where we want to where our online applications want to go to the feature store and say, give me back the feature vector because they're going to make a request in a model. So we do have one large prospect who's trying out our online feature store in DB, and they want to get to 4 million requests per second, and we will reach that. And in that case, we're doing batches of 220 requests in one single operation, and the P99 latency is about 20 milliseconds. Yeah, so that's pretty high-end stuff. There's a question, how do you deal with confidential data, from Vanessa? So Vanessa, in this project model we have here, the data that you put inside a project can be kept confidential and restricted. So what it means, you can have sensitive data inside a project and restrict who has access to it. So if I have this anti-money laundering project here, I have some very sensitive data in it. The only people who have access to it are the members of this project. So you can see it's just me, the admin, and I can add people. If I want to share a data set, so if I want to share, for example, the feature store in here with another project, I can still do that securely. I can say I'm going to share this feature store with the demo ML project, and I'm going to make it read-only sharing, or I can make it read-write sharing, or only the data owners can write and the data scientists can read. So there's different models where we can do sharing. But basically, the data is restricted or sandbox inside this project. I mean, if you have other requirements, what you can also do even in Hopsworks AI is that, which is here, you can create other clusters. So you can create separate, completely separate clusters if you prefer.
One more question. How do you handle data lineage?
Yeah, I mean, the best thing I can do is refer you to, we had a talk at Usenix OpML on what we call implicit provenance in Hopsworks, but what we basically do is, and I think I had this on the last slide that I didn't cover, this slide here. So what we do is we collect metadata at all stages. So every time you write a training data set or a feature group to our feature store, we store metadata in our file system, HopsFS, about that. And we store metadata for any programs that are run, feature statistics. If you do model serving on our platform or run experiments on our platform, we store all of that metadata, and that's synchronized out to Elasticsearch actually. So the provenance queries are all done on Elasticsearch. We can do free text search for all assets, ML assets and metadata in the platform, and it doesn't hit any operational database. It only hits Elasticsearch, which is doing that for us.
Great. I think that was all the questions we had for today. Just a reminder that we'll be sending the video and the slides of the presentation after, so probably tomorrow in the next 48 hours. And if you have any questions, feel free to reach out to us. Thank you very much, Jim, and have a great day.
Thanks, everyone. Bye.